In this video, we solve problem 9.6.016 from Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to consider the following series. We've got n squared plus 8 over n factorial as our nth term of the series. We start with n equals 1 and we go on to infinity. We're adding all of those up. Part A asks us to use the ratio test to verify that the series converges. And then part B asks us to use a graphing utility to find the indicated partial sums and complete the table. I don't use graphing calculators, not on tests or quizzes, but it's important that we be able to find this information. I don't expect you to just write out 25 terms and then add them together. What I expect you to do, or what I would hope that you would do, is use your resources, use technology to find these answers. It's just helping you to understand exactly what's happening when you take partial sums of this infinite series. If you look at the partial sums of the infinite series, you may be able to infer what the sum of the series might be. And if you know that the series converges because of part A, and then you can see that the partial sums are approaching a certain number, then you can have some sense of what that series converges to, even though you haven't proved it by taking all these partial sums. You have a very good sense of the behavior just by looking at the behavior itself and then graphing. And then in part C, we're asked to use a graphing utility to graph the first 10 partial sums of the sequence. I don't think that that's necessary here. We're just going to use the process of elimination to eliminate the 3 graphs that are not appropriate here, and then choose the correct graph. Okay, so let's start with this ratio test. We've got the sum as n goes from 1 to infinity of this, and this is our a sub n. Now, whenever we're using the ratio test, we need to find the next term. So if this is a sub n, we want the term after that, a sub n plus 1, and we want the ratio of the term after that to the term before it, that ratio of those two guys, and then we take the absolute value. And we say if that absolute value is less than 1, well, then that sum will converge. And it turns out, well, in general, it would converge absolutely, but converging absolutely and converging are the same thing because this series only has positive terms. Okay, so that's the plan. Let's do that here. A sub n was n squared plus 8 over n factorial. That means our a sub n plus 1 is this. You just replace n with n plus 1. And now we want to take the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. Now, since these terms are positive all the time, we don't really need the absolute value. And since I'm taking a fraction and I'm dividing by another fraction, I think I'll just multiply by the reciprocal. That'll make the algebra easier. So this first fraction will be a sub n plus 1. And then rather than dividing by a fraction of a sub n, I'm just going to multiply by the reciprocal of a sub n. And the absolute value of those guys is just that product because they're both positive. So a sub n plus 1 is this. Now to simplify this, I would write out that n plus 1. We've got n plus 1 times n plus 1 there. If you would like to, you can FOIL at that point. Or distribute, same thing. So we're going to have n times n is n squared, plus n plus another n is 2n, plus 1 plus 8. So that's going to give us a plus 9, all divided by n plus 1 factorial. So that's the simplified version of a sub n plus 1, and we'll substitute that in over here. And this 1 over a sub n is just this, but we flip it. Okay, now at this point, I'm trying to take the limit of this product. It will be easier to evaluate if I group similar terms together. So I'm going to group this polynomial and this polynomial term, polynomials in M, We'll put those two guys together. And then we can group the factorials together over here. And we're doing that so that we can simplify this and so that we can simplify that. And then when we're done simplifying or evaluating, or excuse me, writing this in a way that it'll be easy to compute the limit, we can just use the fact that the limit of the product is the product of the limits. Okay, now if you're wondering why that's legal, it's because multiplication is commutative. This times this over this times this is the same as this times this. That didn't change. Over this times this. I just changed the order there. It's exactly the same thing. I'm just writing it in a different way so that it's easier to see what happens to this factor and this factor, and then move on from here. Now, anytime you've got a polynomial over a polynomial and you're taking a limit as the variable goes to infinity, one of the easiest ways to determine what the limit is to divide by the highest power of n in the denominator. Now, I know some of you have probably learned the rule that if the degrees are the same, you just take the ratio of the leading coefficients. So the limit of this piece should just be 1, because it's going to be 1 over 1. But I don't want you to just memorize a rule. I want you to understand where that rule comes from. Right now, this is an infinity over infinity indeterminate form. In order to get to that value of 1 that we know is going to be the limit, because this over this is 1, we can divide the numerator and denominator by the highest power of n in the denominator. So we're going to divide everything by n squared there. When we do that, the result is not indeterminate anymore. N squared over n squared is 1, and then we have 8 over n squared over here. Then I've got n squared over n squared, which is 1, plus 2n over n squared, so one of those n's will reduce. You just keep going. So that's what you have right there. And this guy can be simplified as well. If you're not sure, if you're wondering, how does that factorial over something else factorial simplify? What I always recommend students do is substitute in a value of n and see if you can't recognize a pattern just by looking at some numbers. So maybe n equals 3. In that case, I would have 3 factorial over 3 plus 1 factorial, so that's 4 factorial. So that's 3 times 2 times 1 over 4 times 3 times 2 times 1. Notice that 3 factorial is a factor of 4 factorial, and those end up reducing, and you just end up with a 1/4. The same thing would happen if we used n equals 4, but 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. Since 5 is bigger than 4, it's a larger number than 4, it has a 5 factorial has 4 factorial as a factor, so all of those reduce and you end up with 1 over 5. So when I'm trying to simplify this over here, I'm thinking about this pattern and then I'm wondering, how does it generalize? Or I'm thinking about how it generalizes. And we're going to do exactly the same thing here that we did here, but we're just going to do it in a slightly more abstract way. We know that n plus 1 is greater than n. So n plus 1 factorial has n factorial as a factor. Remember how we compute n plus 1 factorial. We start with n plus 1, and then we subtract 1 from this, that's n, and then you multiply. And then you subtract 1 from that, n minus 1, and then you multiply. Subtract 1 from that, and then you multiply all the way down. So 3 times 2 times 1, provided that n is greater than, I guess, like 7 is what I've written here. So we have this in the denominator, but in the numerator, we've got n factorial. Now you don't actually have to write this out. If you want to, you can just say that this denominator is n plus 1 times n factorial, and the numerator is n factorial. So the n factorial and the n factorial reduce, and you're just left with that 1 over, that n should be canceled as well, 1 over n plus 1 there. So you've got this factor times this factor. Remember from Calculus 1, the limit of the product is the product of the limits. And n is going to infinity. So 2 over a very large number is a very small number. That's gone. N, or 9 over a very large number squared, that's going to be a very, very large number. That's still going to go to 0. And 8 over n squared, it's 8 over a very large number squared is going to be a very small number as well. As that denominator gets larger and larger, the fractions get smaller and smaller. And these guys all approach 0, and this guy approaches 0. 1 over a large number is a small number. And as the denominator gets larger and larger, the fraction gets closer and closer to 0. So you have the limit of the product is the product of the limits. This first factor approaches 1 plus 0 over 1 plus 0, which is 1. The second factor approaches 0. 1 times 0 is 0, and 0 is less than 1, so the series converges. And normally we would say the series converges absolutely. I guess we can say that, but saying it converges absolutely doesn't say much since all the terms happen to be positive. That's how we do the ratio test. As far as the algebra is concerned, this part right here, this method that we just used is very common. I know it seems like a lot, but you pretty much do the same thing every time you use the ratio test. So even if it feels challenging at the beginning, I just want to encourage you, after a while, you're going to be doing this so often, grouping similar terms and then simplifying them, that this is not going to be a big deal at all. It's just a little bit of algebraic manipulation. And everything that we're doing here is completely legal because multiplication is commutative, which gets us to this line. Dividing the numerator and denominator by the same thing leads to an equivalent fraction. You know, the factorials always cancel in this way. If you have two numbers, one that's a factorial and another one that's a factorial, the one that has the larger number, that's the one that you want to break down further. So when I saw the n plus 1 factorial and the n factorial, and I knew that n plus 1 was larger than n, then I knew that n would be a factor of this guy. So I break that, or n factorial, excuse me, would be a factor of this guy. So I break that down, and then we can cancel the factorials. And then we just keep using that principle from Calculus 1. Limit of the product is the product of the limits, and that will allow you to compute this last, that last limit, that limit times that limit, which gives you that final limit. Okay, so now the next part asks us to use a graphing utility to find the indicated partial sum and complete the table. Now just to show you exactly what it is we're doing, oh, actually, the calculator that I'm going to use online will show you. So remember, this is our series. I think I just changed my mind as I was talking about that. We've got the sum as n goes from 1 to infinity of n squared plus 8 over n factorial. And we're asked to find the fifth partial sum. So that means we want the sum of the first 5 terms. I just want to show you this just so that you're aware of what it is we're calculating. So when n equals 1, we get 1 squared plus 8 over 1 factorial. And then it's a summation, it's a series, so we add. When n equals 2, we're going to get 2 squared plus 8 over 2 factorial. When n equals 3, we'll get 3 squared plus 8 over 3 factorial. Now, the only reason I'm doing this, again, is to show you what it is that you're calculating when you use these calculators online. When n equals 4, we have 4 squared plus 8 over 4 factorial. When n equals 5, we get 5 squared plus 8 over 5 factorial. So when you add all of these guys together, that is s sub 5. That's the fifth partial sum. S sub 1 is this sum, S sub 2 is that sum, S sub 3 is that sum, S sub 4 is that sum, S sub 5 is that sum. Now, writing this down is very tedious, but you can see that that's just going to be a 9, and then we've got a 12 over 2, so that we got a 9 plus a 6, and then you have 9 plus 8 is 17 over 6, then you've got 16 plus 8 over 6 times 4, which is 24, and you've got 25 plus 8 over 24 times 5. You simplify that and you add them together, and that's the fifth partial sum. So let's go to an online calculator to get these partial sums for n equals 5 terms, 10 terms, 15 terms, 20 terms, and 25 terms. To do that, I will share my screen with you. I found this calculator. It's at www.emathhelp.net/calculators/calculus2/series calculator. I found this by just Googling partial sum calculator. And I think it was the first option. Actually, I didn't use Google. I used DuckDuckGo, which is a little bit, gives you a little bit more privacy. But I've typed in that nth partial, or that nth term, that n squared plus 8 over n factorial. And then I want my starting value to be n equals 1 because that's what was given over here. And for the fifth partial sum, I want to go to n equals 5. And this is what we get. It's actually written in the reverse order. S sub 1, that was 1 squared plus 8 over 1 factorial. That was the 9. When n equals 2, we get 2 squared plus 8. So 2 squared plus 8 is 4 plus 8, which is 12 over 2 factorial. 12 over 2 is 6. When n equals 3, we'll have 3 squared plus 8. So that's 9 plus 8, which is 17, divided by 3 factorial, that's 6. When n equals 4, we've got 4 squared plus 8. 4 squared is 16. 16 plus 8 is 24. 4 factorial is 3 times 2, so that's our 3 factorial, that's 6, times an extra 4, so that's 24. So we end up with 24 over 24, which is 1. And then when n equals 5, we've got 5 squared plus 8, which is 25 plus 8. And that's 33. And we've got 33 over 5 factorial, which simplifies to 11 over 40. It's 33 over 120, which simplifies to 11 over 40. So that's all they did. They just computed a sub 1, a sub 2, a sub 3, a sub 4, and a sub 5. And s sub 5 is the sum of the first 5 terms. And they added them together. If you scroll down a little bit, you can get the decimal approximation that we need for our table here. They wanted us to round to 4 decimal places. So I will say that that's 19.1083 approximately. And then they want us to do that again for n equals 10, or at n equals 10. Well, yeah, we want the 10th partial sum. So we want the sum of the first 10 terms this time. And then it shows you all 10 terms. Those are the first 5 terms. There's a sub 6, a sub 7, a sub 8, a sub 9, and a sub 10. We've got that simplified fraction, but we want the decimal approximation. So that turns out to be 19.1828 approximately. Okay, well, we want the 15th partial sum. So that's the sum of the first 15 terms. And rounding to 4 decimal places again, still gives us that 19.828. And look at that 5th decimal place, 182845. exactly the same to 4 decimal places. Let's look at 20 terms. That's what they want next. All I'm doing is calculating for different values of n. You can see we've got 20 terms on that list. The denominator gets larger and larger. We've got that n factorial in the denominator. And then I love that they don't immediately go to the simplified or the approximation, that they give you that exact answer, that fraction. But again, rounding to 2 decimal places or 4 decimal places, we end up with 19.1828. And then lastly, I want to do the first 25 terms. And so they're still showing you all 25 terms right here. It's a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub 5, 6, a sub 7, a sub 8, a sub 9, a sub 10, all the way through a sub 25. Add them together, that's s sub 25. That's our exact answer, which is approximately the same thing as we saw the last couple of times. So when we're rounding to 4 decimal places, let's look at our paper. We had exactly the same partial sums to this degree of accuracy, starting at n equals 10 and 15 and 20 and 25. So we could probably have stopped right here. We don't need to go any further because we know that that's not going to change any. Okay, so that's how I would calculate that. And I will put the link to that calculator in the description of this video so that you can find it and use it whenever you're solving similar problems on your homework. Then it says use the graphing utility to graph the first 10 partial sums of the sequence, or first 10 terms of the sequence of partial sums. Sorry, I said that backwards. And they give you these 4 options. Now, first of all, the terms of my series are all positive. As we've seen, and we see down here, whenever we looked at the terms in the partial sum calculator, and also when we just write it out, that's positive, that's positive, that's positive. There is never a negative number coming out of this n squared plus 8 over n factorial expression. So when I add up the first 10 terms, they're not going to decrease. When I take this and I add something, it's not going to be less than the number before. So this is not it. As I'm adding terms together and they're positive, they're not going to decrease. So here I take that number and then I add the next number and then I add the next number and the next number and the next number. So that could be it, or that could be it. Then you just have to look at that y-axis. The 10th partial sum was 19.1828. And this is approaching, it looks like it's just a little bit above 19. And that one is a little bit above 10, and that's not what we're looking for. So we'll say, nope, that's not it either. This must be the one. Now you can graph these using Desmos.com if you want to. So if you want to generate this graph yourself, you could. But I would recommend just using the process of elimination for this. Use your common sense. Make sure that you know that when you're adding terms that are positive, the sum should be increasing as long as those terms are always positive, and they were in this case. And then they should be approaching this number here. So even though these graphs look the same, they're not the same because these guys are approaching a number that's a little bit more than 10, and these guys are approaching a number that's a little bit more than 19. So that's the one we want.